Okay, let's jump right into this explainer. Today we're looking at why something completely invisible, air density, is actually the foundational driving force behind massive wind turbines. You know, when we look up at a wind farm, it's so easy to focus purely on the speed of the wind. But today, we aren't just talking theory. We're going to use real site data and uncover how engineers actually build Excel models to calculate the physical mass of the air. It's pretty fascinating stuff.
Before we really get into the weeds, here's our roadmap for today. We'll start with the power of density, move on to the perfect gas law, then the hydrostatic equation, the US standard atmosphere model, and finally, we'll wrap up with the moist air nuance.
All right, section 1, the power of density. Let's get right into it. So it's easy to look at a wind turbine and think only about wind speed, right? But we really have to ask ourselves, what exactly is pushing those blades? Wind isn't just some invisible force. It's a moving fluid made up of gas molecules. So the denser the air, the more molecules are physically hitting the turbine blades every single second. More molecules mean more mass, and more mass, well, that means more kinetic energy to transfer straight into the electrical grid.
Now look at this power equation. See that Greek letter rho right in the middle? That represents air density, and it literally proves that a turbine's power output is directly proportional to it. In this formula, P is your power output, A is the swept area of the blades, W is the wind speed, and CE is your efficiency. But that rho, that's the real kicker. If air density drops by 10%, your energy output drops by exactly 10%, assuming everything else is equal. It's a one-to-one relationship.
To really put this into perspective, think about the Chronoloth wind farm in Ireland. You can't just slap a single flat air density number onto a project when turbines are perched all over mountainous terrain where the atmosphere is physically changing. To predict actual energy yields, you absolutely need site-specific data. So for our calculations today, we're going to model a specific turbine location at an altitude of 216 meters with an average annual temperature of 8.8 degrees Celsius.
Moving right along, section 2, the perfect gas law. So how do we actually build a working air density model in a tool like Excel? Well, we basically follow 3 progressive steps. Step 1 is the perfect gas law, which relates our density to pressure, the gas constant, and temperature. Step 2 accounts for the atmosphere's temperature lapse rate, simply because, it gets colder the higher up you go. And step 3 is integrating the hydrostatic equation to calculate the exact pressure at our specific height.
But before we hit step 3, there's a tiny technicality we should mention. Atmospheric models technically use what's called geopotential height to account for Earth's gravity getting just a tiny bit weaker at higher altitudes. But honestly, look at the numbers. Between true geometric height and geopotential height at a typical 100-meter turbine hub, the difference is a mere 0.002%. It's so marginal that in our practical Excel models, we can safely just use standard geometric height and call it a day.
Which brings us to section 3, the hydrostatic equation.
This is the absolutely crucial equation that models how atmospheric pressure changes as we climb in altitude. The change in pressure, dP, equals the negative density of the air multiplied by gravity multiplied by the change in altitude. Now, when building this out in Excel, engineers don't sit there doing complex calculus. Instead, they break the altitude into small, discrete steps, like 1-meter intervals literally going down the rows of a spreadsheet. They just use the pressure from the row below to calculate the density for the row above. It's a really elegant solution.
Next up, section 4, the US standard atmosphere model.
If you use the model's standardized sea level pressure of 101.325 pascals and a standard temperature of 288.15 Kelvin, you get a baseline dry air density of exactly 1.225 kilograms per cubic meter. This right here is the default number for almost every turbine performance chart out there. But remember our specific site? The one at 216 meters and 8.8 degrees Celsius? Well, if we plug those exact numbers into our Excel model using the equations we just went over, the actual density drops. Relying purely on that 1.225 baseline would literally mean overestimating your energy yield, and nobody wants that. As you climb in altitude, both density and pressure drop off on a pretty steep curve. This is a vital consideration for high-altitude wind farms. If you're installing turbines up on a mountain plateau, you're working with air that is significantly less dense than that standard 1.225 baseline. The blades are physically capturing less kinetic energy at the exact same wind speeds, simply because there's just less air mass heading them.
And finally, section 5, the moist air nuance.
Okay, here's a really surprising fact that often trips people up. Moist air is actually less dense than dry air. Intuitively, we always think of humid days as feeling super heavy, right? But water vapor molecules are actually lighter than the nitrogen and oxygen molecules they replace in the atmosphere. The thing is, water vapor makes up a tiny fraction of total air mass, so the overall effect isn't massive. Still, to be scientifically accurate and calculate moist air density, we have to find the saturation vapor pressure. This curves upward with temperature according to the Hermann-Woebus polynomial approximation. Basically, as the temperature rises, the air's ability to hold water vapor absolutely skyrockets. This means humidity becomes a much bigger factor in hot tropical climates compared to freezing ones.
But let's put this into perspective. When we run a sensitivity study comparing moist and dry air density at a fairly typical cool temperature of 5 degrees Celsius, the difference is incredibly small. The variance between bone-dry air and 100% relative humidity is well below 0.7% in the first 5,000 meters of altitude.
Ultimately, because the density influence of moisture is usually less than 1.7% in normal conditions, say ranging from 5 to 20 degrees Celsius, wind energy professionals can safely assume dry air properties for most practical applications. The math required to perfectly calculate moist air density is complex, and the payout in accuracy is generally so microscopic that it's just ignored in standard yield projections.
But I want to leave you with this final thought. Since higher temperatures dramatically increase moisture's influence on air density, how might shifting global climates force us to completely rethink these standard atmospheric models in the decades to come? As wind farms expand into increasingly hot tropical regions, that safe, dry air assumption might not be quite so safe anymore. Thanks for joining me on this explainer. Next time you feel the wind, remember, you aren't just feeling a breeze, you're feeling the invisible.
This Excel sheet can introduce you how you can calculate the air density. If air density decreases, the expected energy production also decreases. First of all, here we have the constant blocks on the left, gives us the reference atmospheric values like pressure and temperature. So the value includes sea level pressure, P naughts. It's 101,325 Pascal, standard temperature T naughts 288.15 Kelvin, gravitational acceleration G, the molar mass of the air M, and gas constant air. These are the parameters that we should consider into our consideration. So the first equation gives us temperature as a function of heights. In the troposphere, temperature is assumed to be decreased almost linearly with altitude using this constant lapse rate. So lapse rate is 0.0065, and which means about 6.5 degrees Celsius per kilometer. So we can use this constant to adjust the temperature at different heights. For example, here, my reference elevation at my site is 216. Site elevations at my current site would be 440 degrees. So I have measured temperature at the reference site, which is 216 meter, and the reference temperature there would be 8.8 degrees Celsius. Now the purpose, I would like to adjust this temperature based on the given elevation, which is 440 meter. So I have used this equation to adjust my temperature at site. So temperature at site would be 7.344 degrees Celsius. So the first step to calculate the atmospheric pressure based on this formula. This formula gives us how pressure changes with height. The pressure becomes lower as altitude increases because there is less air above the location, so the weight of the air column is smaller. This comes from hydrostatic balance combined with the ideal gas law. So it means now we can calculate the hydrostatic pressure based on the given input G, M, R, L, and T reference, all parameters given here inside this table. So we can easily insert those parameters to calculate the hydrostatic pressure. So it means we have calculated the hydrostatic pressure using the given parameter. So when I click here, you can see the parameters that we have used to calculate the hydrostatic pressure. Now the adjusted temperature and the calculated pressure is there, so we can calculate easily the air density at site. It means once temperature and pressure are known, density can be calculated. In the small box at the bottom, density is scaled from the standard density using the ratio of local pressure and temperature to the sea level reference values. And this is actually equivalent to applying the perfect gas for air. Density is 1.194 kilogram per cubic meter, which is 97.5% in comparison to reference air density at sea. So at this example, the humidity is neglected because it has, as you have seen in video, it has a minor effect on air density calculation.